brighter than the stuff there. Well, I just made an image of disparity, and remember, disparity is inversely proportional to depth. So the brighter values are the closer z's, all right? And the smaller values are further away, and the really small values, which are very dark, are going to be further away yet. Okay, and that's this notion of, from disparity, being able to get to depth.
So you saw how stereo cameras and photographs have been around for a while. Today, stereo plays an important role in entertainment. Have you come across any innovative uses of stereo? Especially something that relates to computer vision? Enter your response in the box to the right. You can enter multiple examples, one on each line. Thank you for your response. I hope you found some examples that involve estimating depth from stereo images, or perhaps novel ways of projecting stereo images so that it's easier to see three-dimensional shapes. I encourage you to share and discuss your examples on the forum.
That ends the lesson on stereo geometry. The idea is that if you have calibrated cameras, if you know the match, then you could compute the depth. So this has been sort of general. The only math that we did was the relationship between disparity and depth. In the next lesson, what we'll do is we'll focus on actually finding the disparity, figuring out which point in one image matches which point in the other image. And that's what you're going to be doing in your problem set. Then we're going to work on calibration, which is determining the relative views. And by the way, you're going to do that in a different problem set. But we're going to break these down one at a time. That's it. Welcome back to Computer Vision. This is going to be the second in a series about stereo. In particular, we're going to focus on what's called epipolar geometry. We had said last time that if we had two images and we knew something about the cameras, if we could find correspondences, given that known relationship, we could find the depth. And we talked about disparity. And disparity was the idea that the location of a point in an image would change depending upon the depth of the scene as I moved my camera. And if I actually had the disparity, I could make a disparity map which tells me how all the points have shifted, and disparity was inversely proportional to the depth, and that's what this disparity map on the right is. But how do we find the disparity? Essentially, given one point in the image, we need to search for it in the other. But our intuition tells us if I know something about how the two cameras are aligned, if you give me one point in the picture on the left, it can't be anywhere on the picture on the right. It has to be somehow constrained in terms of where it can be on the left. This lesson is going to be about those constraints. And then we're going to assume those constraints when we go about actually finding the points in the next lesson. So in general, in the case of two calibrated cameras, we had talked about parallel optical axes, all right, so that they were lined up and the planes were coplanar. But of course, they can be what's called verged. They could be pointed in some particular way. In fact, they don't even have to necessarily be verged on the same point. Usually they are, because we're used to human systems. But what we're going to do is we're going to talk about epipolar geometry, the epipolar constraint, in both of these cases. So let's start it this way. So if I have an image on the left and some point P projecting in that image, the question is, where can P prime, the image of that same point on the right, be? Well, basically, the actual scene point could be anywhere along the ray that contains P prime. Each of these red dots correspond to possible locations along that ray of the actual scene point that's projecting to P prime. Now remember, in perspective projection, one of the things we said was that lines project into lines. So the line containing the center of projection and the ray that goes through that point, that's a real line in space. Okay? That line must project into a line in the right image. So that's the constraint we're going to talk more about. So looking at this geometry a little more carefully, the geometry of two views constrains where the corresponding pixel will be. So the point P that projects into the image, well, it could be out here in the world, that red point P. Or it could be at P1, or it could be at P2, or it could be anywhere along that ray in the left image which projects to that line in the right image. That line is called the epipolar line. This line is carved out by the plane that contains both image centers and the actual point, or just this ray. That plane intersecting the image plane, and the intersection of two planes is a line, that's the epipolar line. Now, of course, the reverse is also true, right? So that same plane corresponds to this epipolar line, okay? These corresponding set of lines, these corresponding set of epipolar lines, provide the constraint that we're looking for. Any point in this image that's on this line, its match must be somewhere on that line and vice versa. And this is called the epipolar constraint. In epipolar geometry, there are a variety of terms that we use all the time, and you should become familiar with them. First is the baseline, which is just the line or the ray in space that joins the two camera centers. The epipolar plane for a given point, I probably should say for a given point, contains the baseline and that point. So this point, this camera center, that defines a plane, and that's our epipolar plane for that point. As we showed before, the epipolar line is an intersection of the epipolar plane of a given point with the image plane. It really should say the image planes because there's always a pair of epipolar lines. Corresponding epipolar lines are, if you have a point on one epipolar line, then, or if you have a point, you figure out its epipolar line, and its matching point must be on the corresponding epipolar line in the other image. Finally, we have something that we haven't talked about before, which is called the epipole. The epipole is the intersection of the baseline ray with the image plane. So assuming the image plane is big enough, right, the image plane is small, it might not, but if the image plane were big enough, it would intersect the image plane there. So you should be clear, right, that since all of the epipolar planes intersect the epipoles, because it contains this ray, that means that every epipolar line will also intersect the epipoles. We're actually going to see that in just a minute. So why is the epipolar constraint useful? Well, we've already said that basically the epipolar constraint reduces the correspondence problem to a one-dimensional search along the epipolar line. In this particular case, we have parallel epipolar lines. We'll see that in just a minute. But the red dot on the left that's located in the window of this beautiful chapel, wherever that is located somewhere in this epipolar line on the right. So I search for the middle of the window. I don't have to look all over the image. I'm just looking along the corresponding epipolar line. So what do epipolar lines look like? And we'll consider two cases. There's the general case on the top where we've got verged cameras, and then there's the special case where we have parallel optical axes. In the verged case, drawn here, you can take a look at the epipolar lines by considering a couple of different points. So remember, each point defines a pair of epipolar lines, and here they're drawn. And so here's an example of epipolar lines of two verged cameras. And what that means is that, for example, this point here, since it's on this, happens to be on this line, must be somewhere on that line, and in fact, there it is. Okay? And this point here. Now, only a few lines are drawn on here. Of course, if I was looking for this point here, there is some epipolar line, because there's some point here that defines an epipolar plane, and there would be a corresponding epipolar line on the other side. We've only drawn in a few of them. So here's a question for you. We said that all the epipolar lines converge at the epipole. Well, where's the epipole? Well, let's take a look at just this image on the right. The problem is that this image ended here. If this image were huge, this line and then this line, here's where they would intersect. Okay? So the problem is that the image, if you will, is sort of cropped. The image sensor is too small to actually find the epipole. The epipole is a mathematical construct that's the intersection of the baseline with the infinite plane that contains the image plane. So that's why the epipolar lines look like they would converge, but they do it off the screen. Now, let's consider the case where we have parallel image planes. It's a little hard to see here in the picture, but the idea is I've got two image planes. My centers of projection are sort of out here, and any point defines a plane that intersects these image planes, and it's what's called actually a pencil of planes. These planes rotate around that baseline, but we have parallel image planes. What do the epipolar lines look like? Well, they look like this. In this particular case, because of how they're shifted, they're these horizontal lines, and you can see that for the corresponding 3 points located on that chapel, they land 4 points, sorry, that they land somewhere on these epipolar lines. So if the epipolar lines are all supposed to intersect at the epipoles, and here we've got these horizontal epipolar lines, where are the epipoles? Well, as somebody once explained to you somewhere in some metaphysical space, sometimes various hallucinogens were involved, parallel lines intersect at infinity. Okay? So essentially the epipoles are out at infinity. And if you're not sure about that, travel to the Himalayas and ask somebody high up on a mountain or just high up anywhere. I don't know if I'm allowed to say that. Just ask them about parallel lines. And the idea is that parallel lines here essentially are infinity. One way of thinking about that is as the two planes get closer and closer to being parallel, the epipoles keep moving further and further. And so when you take a limit, when they actually become parallel, then the location of the epipole is at infinity. That brings us to a quiz. Let's consider these two stereo pairs. We have the top one, which you know the cameras are verged because those lines intersect. But the bottom one, I'm going to tell you, is from an image pair, stereo pair, that has coplanar image planes. And the question is, how do you know that image B has a parallel image planes? And I'll give you three choices. A, the epipolar lines are horizontal. B, the epipolar lines are parallel. And C, because I just said B had a parallel image planes. Well, you might think, and I'll go back to here, that it's because they're horizontal that we know that they're parallel image planes. But actually, parallel image planes mean that the epipolar lines are all going to be parallel. The only reason they're horizontal is because I happen to be holding the camera in such a way, the pair of cameras, that the baseline between them is horizontal with respect to the vertical in the image. Right? So basically, if I had held things this way or rotated my one camera that way, I would still have parallel epipolar lines because the epipolar lines are defined by the geometry of the camera center and the point. That is the plane. They just have to be on a plane, but I can shift them up and down. I can rotate them, and that will rotate my parallel lines. So it's not the horizontal epipolar lines that tell you that they're coplanar, but the fact that they're parallel. That ends the lesson on epipolar geometry. In the next lesson, what we're going to assume is that we know the epipolar lines. In fact, most of what we'll talk about will use horizontal, parallel, lined up epipolar lines. And then we'll go about solving the correspondence problem. Welcome back to Computer Vision. Today we're going to talk about stereo correspondence. Up until now, we've defined the epipolar geometry that talks about how the two views relate, and how if you have a point in the left image, then if you know the camera's relation, it's a one-dimensional search. And in general, the epipolar lines can be, well, arbitrary, not arbitrary, but skewed in a variety of ways and located. But today, in order to make life easier, we're going to assume a bunch of simplifying assumptions. For example, we're going to assume basically the geometry that we drew out last time of parallel or coplanar, actually, image planes. We're going to assume the same focal lengths of the two cameras. We're going to assume that the cameras are horizontally aligned at the same height, and that the images are pulled out such that the epipolar lines are horizontal and that they are in fact lined up. So a XY location in one image is at a different X, but the same Y location in the other image. So look, that's a lot of assuming, and for real stereo, you wouldn't be able to do that. You'd have to do a rectification of the image first. We'll talk about that a couple of lectures from now. But for now, we'll make these assumptions which will allow us to attack the correspondence problem more easily. And in fact, it's the way you're going to be doing correspondence on the problem sets. So what is the correspondence problem? Well, basically, the epipolar constraint constrains what our solution is, but it doesn't solve our solution. So here we have a bunch of points in the left image, and we know they lie along the epipolar line in the right image. But the question is, what are the matches? And here in hypothesis 1, 2, and 3, coded in gray here, you can see these are different possible matches. And so for each point in the left image, we have to decide what the match is in the right image, or vice versa. So to help solve the correspondence problem, what we need are some additional constraints. The epipolar constraint was a hard constraint. That is, it must be true, it's enforced